So today we are going to be talking about the BB84 protocol, which is what's called a quantum key distribution scheme. So most of us are probably familiar with Shor's algorithm and with the use of quantum computing in the arena of attacking cryptographic protocols. I'm guessing fewer of us are familiar with the use of quantum mechanics and quantum technologies for the other side, for defending cryptographic protocols. And the idea, the promise of these sorts of protocols is that they allow us to create cryptographically secure mechanisms which are impervious to any degree of computational capacity or mathematical sophistication on the part of the attacker. So whereas RSA and Diffie-Hellman and all of our public key cryptography friends are built on top of tractability assumptions that says, for RSA, for instance, that the discrete logarithm is hard, we can theoretically, and actually in practice people have built these things, we can build systems which are immune, regardless of how many computers Eve has, regardless of how fast they run. She cannot get information out of our protocol if we run it correctly. And that's why these will tend to be called unconditionally secure in the literature. And we're going to be talking specifically about BB84, which is one of the most popular QKD schemes around, originally proposed in 1984 by Bennett and Brassard, hence the name BB84. And we're gonna do the talk in two parts. First, we're going to go through what I'm going to call textbook BB84, and that's by analogy to textbook RSA, which sort of gets the gist across, covers all of the important points, but neglects several other practical important details, which make it hopelessly insecure if you were to just roll it out directly as is. Once we've got that sort of gist of the scheme under our belts, I'll go through a couple of different things that you need to take care of in order to take this textbook BB84 and turn it into something that you might be able to run in production, actually protecting traffic. So we're going to be making heavy use of light, and specifically photons in BB84. It'll therefore be helpful if we can remind ourselves a little bit of how light works. And at the most fundamental level, we probably all recall that light is two waves that always complement one another. You've got one in an electric field and one in a magnetic field. Being waves, they're going to satisfy the general wave equation, which tells us that the Laplacian of your waveform is going to be equal to the second time derivative of your waveform. Put another way, the sum of your spatial derivatives is going to equal your time derivative. Sorry, sum of your second spatial derivatives will equal your second time derivative, possibly up to a constant factor. I've omitted that here because you can usually take care of that with appropriate unit selection. And then these aren't just any old wave. These are electromagnetic waves, which means they're going to satisfy additionally Maxwell's equations, which, if I recall correctly here, the first two on this one line here are flux conservation. And then the next two are going to be Faraday's and Ampere's law, which say that changes in electric fields induce magnetic fields, and similarly that changes in magnetic fields induce electric fields. So if you want to know how light behaves, what you do is you get a set of initial conditions, you get this pile of differential equations, and you solve it, which I haven't solved a differential equation since I think it was freshman year of college. And that's near on a decade ago. And I'm not going to do that now for you. Neither am I going to ask anybody to do it. What I am going to do is I'm going to direct us to a very useful simplified model of light, which turns out to be quite useful. This is sort of the infinite frictionless plane of optics. And that is the harmonic planar wave, which this actually can describe a lot of light because Fourier transforms are powerful and useful, and waves can be superimposed with one another to create superpositions. But what we see here is that if we take a sinusoid in the E wave and let that traverse in what we have labeled here as the Z direction, then if we also pair that with a B wave, which is orthogonal, so we've got this in sort of the X axis, this on the Y axis, then we can create this wave here, and this will satisfy Maxwell's equations as well as the general wave equation. And in fact, we can we can experimentally generate light waves which create this specific pattern we cheat a little bit. The mathematical formalism for this one, when you usually look at it, assumes an infinitely long light wave. That's not going to be what you see in practice, but we can create things that look an awful lot like this in the lab. And what's going to be very useful to us is to identify the plane in which the E wave is sitting. And we're going to call the orientation of this wave the light's polarization. So you can imagine that you can take this entire image and rotate it 360 degrees, and any one of those will still satisfy Maxwell's equations. Any of those will still satisfy the general wave equation. So there's nothing special, of course, about having the E wave aligned with your x-axis or y-axis. We can align it with anyone we want, and we can put it anywhere in between. And that's going to be useful later. Now, I mentioned that polarization is a thing we're going to be working with. If you're going to use a theoretical property of light, polarization, it's useful to have ways to experimentally interact with polarized light. And the way we're going to interact with it is something called a polarizer, which allows us to filter light in accordance with its polarization. And specifically, the more aligned the polarizer is with the incoming light, the more it's going to let through. And then the more unaligned it is, the more it's going to dim it. And that is going to follow a very reliable rule, at least in the ideal case, called Malus's law. And that's going to say that the intensity of the outgoing light is going to be multiplied through by the square of the cosine of the angle between the light's incoming polarization and the angle of the polarizer that you have set up. And this isn't really important to us here, but it also turns out that the light coming out will always be aligned with that polarizer. So our little example here, we have light coming in at about 45 degrees. So we have this theta here. We would expect cosine squared of 45 degrees. That's 1/2. So we will get light at intensity about 1/2 coming out of this polarizer. And moreover, it will wind up being aligned with the polarizer's orientation. So that's classical optics. This is a talk on quantum key distribution. So we need to move into the quantum realm if we're going to do that. And we will recall, I assume all of us, that electromagnetic radiation, the quantum unit of that is a photon, and that your quantum things generally have all of the aspects of your classical thing. In this case, polarization is still an attribute of a photon, or possibly you have superpositions of different polarizations because quantum mechanics is complicated. If that doesn't mean anything to you, don't worry about it. It won't be important for the rest of this talk. What will be important is that you can't dim a photon. Your photon is either going to be intercepted, it's either going to be absorbed, or it's going to be transmitted when it interacts with a medium. And this, is a bit of a problem for Malus's law because it posits that light is dimmed when it passes through a polarizer. What we need then, if we're going to merge our classical regime, what we've observed there, and our quantum regime, which posits that all of this EM radiation is moving in indivisible photons, is we need a mechanism which, when you add a whole bunch of different events together, they on average create the classical behavior. And as is so often the case in the world of quantum mechanics, that thing which bridges your quantum stuff can't happen in between. It has to either happen all the way or a little bit, all the way or not at all. The way that we bridge between that reality of quantum mechanics and the analog nature of the classical world that we're used to is probability. God is going to roll some dice, and the dice he's going to roll are going to be loaded in accordance with the angle between the polarizer and the incoming photon's polarization. So this is exactly the same as Malus's law before, which said the intensity gets dimmed according to cos squared theta, only now it's the photon gets through with probability cos squared theta. And those of us that recall our trigonometric identities will remember that sine squared plus cosine squared is always 1. So our probabilities do sum to 1, and we're okay there. All right, one last piece of quantum mechanics that we need to review before we can start getting into sort of computer sciencey things is the no cloning theorem, which states loosely that when we interact with a quantum entity, including a photon, we are going to damage it in some fashion. And more precisely, it's impossible to perfectly capture and reconstruct a photon or other quantum entity that you're working with if it has an unknown initial state. This is frequently misunderstood to imply that any interaction with a photon destroys it completely. A better way of thinking about it would be that any interaction with a photon is going to put some miles on it, and it's going to do some wear and tear, and maybe it'll break it. Because in fact, you can approximately clone photons, taking advantage of lasers. If you feed one into an inverted medium, there is a greater than even chance that you will get out multiple photons on the other end, with those multiple photons having all of the same quantum characteristics of the incoming photon. That said, there are still, even when you accept approximate cloning, upper bounds on the fidelity of how well you can clone. So while we can't just come in and say, you can't touch the photons, we can come in and say, if you touch the photons, you will probably be detectable doing it. And that's going to wrap up our quantum optics refresher. Does anybody have any questions they'd like to ask at this point? All right. If so, we're going to roll on into the BB84 protocol itself. And we're going to start by defining a notion of qubit bases. And we're going to notice that by Malus's law, we have deterministic behavior, even with individual photon measurement. At theta is 0 and theta is pi over 2. So if you have perfect alignment, it's always going to go through. And then if your polarizer is right here and your light is right here, if they're orthogonal, it's never going to make it through. And this suggests to us a mechanism for sending bits as individual photons. So what we're going to do is we're going to map vertically aligned light to a 1. And if it's horizontally, we're going to call that a 0. And an important thing to note here is that which way is up is purely a matter of convention. We mentioned earlier that you can perfectly well rotate around the E wave and create valid light polarized in any direction. And similarly, you can rotate your polarizers. So an interesting question for us to ask is, if we've got an experimental setup, we've got a laser and some polarizers, and we're sending vertical and horizontal light, and that is our 1s and 0s, and that's all going well. But then we play a little bit too hard with our Balmer drip, and we come in drunk one day and we stumble over our machine and we knock it out of kilter. So now our laser is still actually lined up perfectly straight vertical, but our polarizer, which is receiving it, we've knocked it off a little bit. Now it's got a phase offset of phi between those verticals. And what's going to happen there, it's pretty easy to see by Malus's law, is that we're going to have a bit flip possibility. And that bit flip is going to be in accordance with the square of the sine of this phase angle phi. And just to take a concrete example, if we've got a 1 coming in and then this slight angle here phi, then we have still a cos squared phi chance that it gets through just fine. But that remaining probability, that remaining sine squared phi chance, is going to exist that it gets absorbed and therefore treated as a 0. So it will have been flipped. So this implies that if I'm measuring in the wrong basis, I have an unavoidable chance of corrupting the bits that were encoded in this basis when I decode them with this offset of phi. All right, and that does it for preliminaries. Let's talk about what the protocol actually looks like. So Alice is going to start by selecting a random sequence of bits and of bases. So 0s and 1s randomly chosen. And then we have each of these blocks here is either blue or red. A blue block is going to be what I call a rectilinear basis. So that's my 1 is up here, my 0 is here, vertical and fine. And then the red blocks are going to be what's in what I call a diagonal basis. So that's when I take the whole works, all of my polarizers, and I just rotate them 45 degrees. And what you'll notice is that by rotating it by 45 degrees, if we send light from our blue basis to our red basis, from rectilinear to diagonal, it's going to corrupt it about half the time. And in fact, if I've done it perfectly, it'll corrupt it exactly half the time. So the other protocol participant is going to be Bob, as usual, and Bob is going to start by selecting a random series of bases. Nobody's communicated anything yet. We're just working inside our own memory to create values. And Alice is going to start transmitting photons. And in the first case in our example here, we've got a blue basis to a blue basis. Everything agrees. We're working in an ideal case. There's no chance of corruption. Bob gets a 0 because Alice sent a 0. In the next one, Alice is sending from a diagonal basis to a rectilinear basis on Bob's end. And sine squared of pi over 4 is 1/2. There's a 50% chance that that's going to be corrupted in transit. In this case, it didn't. Probabilistic stuff happens that way. Sometimes you get the bit successfully, sometimes you don't. The next one, she's going to send rectilinear to diagonal. And in this case, again, it could fail. And it happened to, just luck of the draw, get flipped in this case. And it goes on, so on and so forth, until you've transmitted sort of all of the qubits you're interested to transmit. In this case, 8. So now what we've got here is Alice has a list of bits, Bob has a list of bits, but a goodly number of them are probably wrong. And actually, there's literally no information that Bob has about what Alice sent in half of those bits. So wherever our bases did not align, so we've got red and blue, blue and red, anywhere where that happens, there's a 50% chance that Bob has the same value that Alice does, and a 50% chance that he doesn't. That is literally no information. He's at maximum surprise about what Alice is using his posteriori measurement. So we're just going to throw all those bits out. They're not of any use to us. And now we have a sequence of bits. Okay, these were successfully transmitted. But we haven't done anything other than just transmit bits over a wire yet. So here's where the no cloning theorem starts to come in. We're going to sample a sequence of our remaining bits completely at random, and we're going to compare their values. And they all line up here. 1 is 1, 0 is 0. And we're therefore going to declare, because there were no errors, that the protocol succeeded after we throw those out, right? We just announced some bits. Eve now.
Alan.
Yes.
By the way, hi, how's it going? Quick question for you. What is the purpose of having different phases here other than being obtuse? Is it just to show that there's an attacker?
Yes. So I think the next slide is going to answer that for you.
Okay, never mind then.
The slide after next. If it's not clear by the end of this section, please ask again.
Okay.
All right, so we go ahead and redact those sampled bits because we just announced them publicly, and we don't want Eve to take advantage of that very easy attack surface that we've just provided. And that leaves us with exactly these 2 remaining bits that were transmitted, but that are theoretically perfectly secure. So this is a summary for anybody that wants to keep a copy of the PDF open, and this may be useful reference throughout the rest of the talk. It describes exactly what we just went through in the pictures, so I'm not going to talk through it again. But intuitions for why this would work. First of all, our rectilinear and our diagonal bases were chosen to maximize the chance of corruption. They're what's called maximally conjugate. So if I decode a rectilinear bit in a diagonal basis, I'm going to flip it 50% of the time, which is the highest chance of corruption you can get before turning a NOT gate on is going to repair things. And as a consequence, because Eve doesn't know the bases that are being sent and received in, if she starts playing intercept forward attacks, she's probably going to corrupt some bits. There's going to be a 50% chance that she's in the wrong basis, either between herself and Alice or between herself and Bob. And there's going to be a 50% chance that she corrupts because the encodings don't match up, which gives us, if Eve is being sort of obtuse and naive about her attack, about a 25% chance that when Eve is sniffing, she's going to introduce a corrupted bit. So this isn't going to allow us to stop Eve from snooping on us, but we can tell when she does. So this is in marked contrast to something like Diffie-Hellman, where we expect that the protocol will always succeed, and Eve just can't figure out what we've done because math is hard. In this case, we're going to try to exchange keys, and we're either going to succeed or we're going to fail. And when we do succeed, we're going to be quite confident that Eve wasn't in the room listening. So that does close up the section. Did that answer your question, or do you want to re-ask it?
No, it's all good. Thanks.
Okay. And this is actually a very good point to break for questions because we're about to move into some of the hairier details. of BB84. Does anybody want to chime in with questions about the gist of the protocol? 3, 2, 1. All right. So let's start talking then about our first problem that we've overlooked, which is that we are going to observe benign quantum bit errors. That is to say, we're going to have a quantum bit error rate, or QBER, greater than 0 generally. And this stems from the fact that operating on single quanta is really, really hard. This is going to bite us, I think, 3 times. 3 out of our 4 subsections is going to eventually ultimately stem from the fact that photons are very small and wee little things are hard to work with. So when Eve is interfering, we are assured that at least for a large enough number of bits that we're transmitting in a significant degree of interference, we have assurance that Eve is going to introduce some bits. Even when Eve isn't interfering, though, some of our bits are going to be scrambled. And if you have a secret, which is mostly the same between Alice and Bob, that's maybe kind of useful, but it's not nearly so useful as having a secret which is exactly the same. So we're going to need to, in some fashion, take the secrets that Alice and Bob have that are largely correlated, and we want to get them so that they are, at least within some negligible probability, definitely the same. And the approach we're going to take in this talk to that is going to be built on top of Hamming error correction codes. And we're going to build that up in the next couple of slides. And we're going to start with single error detection. So I'm going to assume 4 bits here. Really, any power of 2 will do. And so we've got D1 through D4. And we want simply to detect one single bit flip. Don't want to do anything useful with it. We just want to know that it happened. And the standard approach that any of your undergraduate professors would give you for this is, why don't you stick a parity bit on the end? So we're going to take a new bit, P1, and we're going to define it as the XOR of D1, D2, D3, D4. And what we will see if we do that is that if we retrieve our new code word, D1 through D4, P1, and it has odd parity, then between us storing it somewhere and reading it back, at least 1 bit must have been flipped. It could be 3, it could be, well, it can't be 5. We don't have, oh, yes, it could be 5. We have 5 bits to flip. Could be any odd number of bits that were flipped, but if we have exactly 1 error, we will definitely detect that. And I'm going to introduce some notation here, which allows us to write this idea of having a parity bit more succinctly and allows us to write more complicated parity checks fairly succinctly, and that's a check matrix. So we're going to have this matrix H, which if we multiply into our code word is going to create our parity checks. So our total parity bit is checking every bit in the code word. So if I go ahead and I multiply this matrix into a code word vector, a bit vector of this form, then I'm going to get exactly this parity check out. So, and that takes advantage of the fact that if you are doing arithmetic mod 2, XOR is exactly your addition operation, and is your multiplication operation. So 1 and thing is thing. So this is just 1 and this plus this plus this plus this plus this. And that gives us whether or not we had a bit flip. Okay, so single error detection, really easy. What now if we want to not just know that our word was corrupted, but that it was corrupted and which bit we need to flip to put it back the way it should be? First thought here, if parity got us this far, can it get us further? And we're going to be a little bit clever about it. We're not going to have 6 total parity bits because that's not going to do anything. Each of them encodes exactly the same information. We are in fact going to have different parity bits covering different parts of the word. So maybe parity bit 1 covers data bits 2 and 3, and parity bit 2 covers data bit 4. That's not actually the scheme we're going to use, but that's the idea. And the scheme we actually do use is going to need an additional requirement here, is we're going to make sure that every bit in the code word is covered by a unique combination of parity bits, so that when we do our check using the same check matrix, well, the same style of check matrix as we did in single error detection, we can look at which of our parity bits are upset, and then that will tell us deterministically which bit must have been flipped in our code word. And we don't have to come up with this ourselves. This was solved by Hamming for us in 1950. And what he does is he abuses powers of 2. So we're going to insert a number of different parity bits. And the way we're going to do it is to bootstrap, we're just always going to start with a parity bit. And then our first parity bit is going to have what I'm going to call a stride length of 1. And it's going to cover everything within its stride length, ignore everything within its stride length, cover everything within its stride length, ignore. So on, off, on, off, on, off, on. And then once we finish the first stride for the last parity bit added, we're going to add a new parity bit. So we've just done parity bit 1. Okay, next bit, parity bit 2. Okay, we've already left the first stride for parity bit 1, so we need to introduce a new parity bit. So parity bit 2 follows immediately. And then the stride length for parity bit 2 is going to be 2. So we're going to be on, off, on. And then we're going to move into our next slot. We have still in this third bit position, we're still inside of P2's first stride. So that's actually going to be data bit. But then the next one is the end of its first stride. So we need to add a new parity bit. That's going to be parity bit 3. And that's going to be on. If we had more bits that we needed to cover, it would be off, and so on. And this last stride covers the entire remainder of the code word. So then we get D2, D3, D4. And an important result when we do this construction, I'm not going to prove it, but it is true, is that we see this powers of 2 construction guarantees that we have exactly our every bit is covered by a unique combination of parity bits constraint that we wanted before. Right, so the first bit in our code word, which happens to be parity bit 1, that's covered exactly by parity bit 1. And then if we look at our second bit in the code word, which is going to correspond to this column here, it winds up being covered only by parity bit 2. And then the next one, parity bits 1 and 2, and so on and so forth. But you'll note that there's only one 1, 0, 0 here. There's only one 1, 1, 0. So each of these has a unique bit string, which tells you which parity bits affect it. And therefore, if I multiply H into a code word and I get out 101, then I know, oh, it must have been the check corresponding to this 101 here. So it would be 1, 2, 3, 4, 5. Bit 5 would be the unhappy one. And then we flip that one, and theoretically, we've corrected our single error.
Alan, are the parity bits in this quantum bits, or are they classically?
These are classical bits at this point.
Okay, thanks.
Any other questions before we move on to our next step in error correction? Alrighty. So we have single error correction, we have single error detection. Can we get single error correction and double error detection? Yes, and in fact, we can just glue the two together, and we wind up with a full so-called SecDed scheme, single error correction, double error detection. We do need to be a little bit careful about how we handle these things. It's not a simple check matrix, just look at the parity bits anymore and match them to the corresponding column. Now we have to look at first, okay, how many, first case we can have here, no errors. We have a healthy code word. In that case, all of our parity checks are going to report even, everything's happy, great. If we have a single error, what we're going to see is that our total parity is going to report odd, and the single error correction parity is going to tell us where the flip was. And then if we have 2 errors, the total parity is actually going to say everything's hunky-dory, even though it's not. But at the same time, the single error correction parities are going to claim that there's a location in need of fixing. We put that in quotes there because the single error correction parities are going to be pointing at the wrong spot. So in the event that you do detect 2 errors in a SecDed scheme, you don't try to correct. You just say, oop, something went wronger than I can fix. And this scheme is what's commonly called Hamming 8-4. Again, you can do it for any power of 2. Just extend the construction on in the same fashion until you hit the desired size of code word. And we have the exact same code word to start with, P1, P2, D1, P3, D2, D3, D4, and then we just glued this P total on the end, and that's going to correspond to this extra all ones row at the bottom of our check matrix. Okay, any questions there? Excellent. So I will add one more piece of nomenclature, which I will probably accidentally lapse into in the next slide, which is that when we multiply this check matrix H by a code word X, the result HX is called a syndrome. Alrighty, so here is going to be the Winnow protocol for error correction with BB84. It's not the only one, but it's the one that we're displaying here. And the idea is to start with, what if we just pretended all of the qubits that we have left after we sift out basis mismatches? What if we just pretend they're sected code words? What's going to happen then? Well, they're not. So if we just pretend and do corrections, like if we have Alice take her block A, hit it with her check matrix to create a syndrome HA, that syndrome is almost always going to want to correct something. And Bob is similarly going to have corrections that the sected scheme is going to want to make, because these were not encoded as sected, and there are a great many more invalid code words in a sected scheme than there are valid. But what if we compare just the differences, and specifically the differences between these syndromes? So if Alice has block A, Bob has block B, and they've both computed syndromes, what happens if we have Bob apply sected correction using the XOR of these two syndromes rather than just his own syndrome? And the first thing we see there is that, okay, well, A and B are highly correlated, right? The only reason they should have errors is because of one-off bit flips resulting from measurement failures. So this code word should be about 0. And when I say about 0, I mean the Hamming distance to 0, the number of bit flips necessary to make it into a 0. Very few bit flips are required. Obviously, if you try to treat this as like a 2's complement number, it could be very large if you just have one bit flip and a higher order bit. And we'll note also that 0 is a valid code word. So if we do correction on A XOR B, it's going to tend to want to correct toward this 0 code word, which corresponds to A and B being equal. So that's good. The next thing we're going to note is that HA XOR HB, so if we XOR our two syndromes together, that is exactly the same as XORing our two blocks first and then taking the syndrome of that. And this is simple distribution of matrix multiplication over addition, which we're all familiar with, hopefully anyways. And so what we've got is that this syndrome here, this XOR of HA and HB, that actually tells us how to flip B, or we could flip A, in a direction that will tend to make A XOR B 0. Put another way, if we just reconcile the errors implied by the XOR of our two Hamming syndromes, we will tend to reduce the number of bit errors between Alice and Bob. So that implies then our error correction scheme. Alice and Bob are going to break their bits into a bunch of sected code words, not valid sected code words, but they're going to treat them as sected code words. And we're going to start with an optimization. We're not actually going to exchange the whole syndrome to start, because when you're doing sected, if you have an even number of errors, you never do anything. Either there are no errors to correct, or there are too many errors to correct, and you're just going to make things worse. So we start by actually just exchanging the total parities, and where the total parities between Alice and Bob agree, we can just ignore those blocks for the remainder. For the rest of the blocks, for the ones where we have an odd number of errors, and hopefully exactly one, Alice is going to send Bob her syndrome for that block. Bob is going to apply single error correction using this XOR of HA and HB, and that will probably reduce, that will with high probability reduce the number of errors by 1 between Alice and Bob's stuff. We've just announced a bunch of information about our secret. Eve can't have that, so we're going to throw away all of the parity bits, whether they were part of the main syndrome or just total parity. We're going to throw those all out so that Eve can't learn anything. And then we're going to go ahead and we're going to shuffle our bits before we go on to the next round. And this is important because if you have the same code word and you just repeatedly try to apply Hamming error correction to it, and it keeps going back saying, you have an even number of errors. You have an even number of errors. You have an even number of errors. You're never going to get out of the loop. You're never changing the bits that are being XORed. So we shuffle everything around to try to make sure that we get any twosies inside the same code word. We want to split them up, break up the buddy system. And then we're going to go back to step 1, and we're going to repeat this procedure n times, where n is a configurable parameter that we have selected such that the probability of errors surviving is negligible. And that does it. That's our error correction scheme. Any questions there?
How was is the shared seed, since it's intended to prevent an infinite loop in essence? Is that not considered secret material?
Yes. So everything that we have discussed so far is going completely in the clear. So, and that's a very good question. The reason that you can announce this seed to do that shuffling, because the shuffles do have to be coordinated, otherwise you're doomed. The entire purpose of that, it's not any sort of fuzzing information to hide information from Eve. It's literally just, if I have these two bits in the same code word, I'll never get them gone if I don't separate them. So that's all it's doing. Eve can know about the fact that I separate errors. The information that is actually going to potentially be useful to her if she's trying to snoop in the future is these parity bits inside the syndrome, because that gives you partial information about what the code word was. So those we do have to throw away.
But so how do we get? I think maybe I missed something. How do we get stuck if the error bits are sort of probabilistically present?
So the error bits are probabilistically present, but once you've done your initial send, right? If you have a, it's entirely possible. Let's say we're doing 8-bit blocks. So it's entirely possible that your first 8-bit block, let's say, has 2 errors in it. Just happenstance, those are the ones that got flipped. And then if I repeatedly apply the same procedure to that same block over and over and over again, and I never change the block because I say, oh, it's even, whatever, then those 2 errors are never going to get removed.
Okay, because the calculation's being reperformed, it's not being resent at this point, though.
Could you rephrase that question?
Well, so if I resent the same block via quantum means, right?
Yes. So we are in a completely classical world at this point. Sorry if that was not completely clear. So we do.
I thought the data bits were still quantum.
Yes. Let me clarify that point. Thank you for asking the question, because I'm sure at least 2 or 3 other people had the same confusion. We have one stage here, which actually involves. I hate that Chrome doesn't let me use the navigation links. This stage here, this is the only part where we're using a quantum channel, right? Where we have our random bases and we send our bits across and some of them get corrupted. From this point on, we are using classical information techniques to try to make those raw secrets useful.
Okay, and then none of these bits that are being sent are any of the parity bits either. Those are purely data bits.
So those bits are going to be both our parity bits and our data bits.
We're pretending that it's.
We're pretending, exactly.
Okay, got it. Cool, thanks.
Thank you. Very good question. Again, if one person has it, I'm sure several others do as well. Any others before we move on to the next hiccup that we want to correct? Alrighty. So let's talk about privacy amplification. And once again, the root of our problem is the fact that quantum bits are hard to send. And when we send them, we're going to have some amount of legitimate error, which is a problem because if we want to actually be responsible about handling our data, we need to assume that every error that occurs is the result of Eve doing something naughty. Otherwise, she could conceivably modify the environment between side A and side B of my transmission to make it better when she doesn't want errors to be detected, and then we only detect the errors that are the result of her snooping. So this poses a problem for us. One of our steps, I believe our last step in our textbook BB84 was look at how high the error rate is. And if it's too high, restart, abort. In a system with real error, that gives us 2 choices. We can either set the acceptable error rate at 0, in which case we will never actually succeed in negotiating a secret, or we can set it greater than 0, which per our paranoia argument implies that we're allowing Eve potentially to have partial information on our secret, which is not okay. We're aiming for unconditional perfect security here. That's not going to cut it. So we have 2 things that we need to do. First, we're going to need to figure out some way to get a bound or an estimate of how much information Eve can have on our key. And then we need to figure out a way to scrub out that many bits from our secret, even though we don't know which ones she has that information on. And in fact, it could be probabilistic over several different bits. So the first step, first thing first, is going to be parameter estimation. We want to figure out how much information Eve has. And we are going to use that measured quantum bit error rate, which we are going to note QBER here. We're going to use that in determining how much information Eve might have. And we're going to note that if Eve is eavesdropping, then that measured QBER is going to be a scaled binomial, parameterized both by the number of bits we're interacting with, and then P is going to be the probability, the sort of true underlying probability that Eve introduces an error. And that's going to be informed by how clever Eve is with her snooping mechanism, how many bits Eve bothers to intercept and resend. Those two should be the big main ones. I might be forgetting something. But this underlying error parameter can be used to create a theoretical bound on the amount of information that Eve has gleaned from your secret. So there is a link at the end of this presentation to a Springer paper, and they go through it in considerably more detail. But the number that we're going to care about here is 2 root 2. So if Eve has introduced 5% error rate, if we observe a 5% error rate in our transmission, our quantum transmission, then we're going to say, okay, Eve can't have more than 2 root 2 times 5% of our key worth of information. And that is, of course, assuming that 5% is the true P, not just our sampled P. So if we can just figure out what this true underlying probability of bit flip is, we can get a bound on how much information Eve can have. Okay, so how can we do that? First idea, what if we just use our measured quantum bit error rate, like I was implying just a few seconds ago? We saw 5%, treat P as 5%. And that's a terrible idea, because if you have a binomial distribution with a large N, about half the time you're going to find yourself right of mean, and about half the time you're going to find yourself left of mean. So this is not anywhere near sufficiently pessimistic to allow us to say, no, Eve certainly doesn't, or at least only has negligible probability of having more information than I think. Okay, I love Bayesian formulations of things. So the next thing that occurs to me is, can I use this a posteriori information I have, this measured quantum bit error rate, and can I pick my p hat such that I believe the probability that the true p is larger than that p hat is less than some negligible quantity epsilon? That's hard, because if I want to do that, I need to start mucking about with uninformed priors to put on P. I don't have a reasonable way of guessing, okay, well, how much snooping is Eve probably going to do without any information? Like, I don't have that. Maybe she's at 0.1, she's snooping. Maybe she's at 0.9. I have no clue. And figuring out a safe way to do that is subtle at best. So the Bayesian formalism is going to be tough to work with. Which basically leaves us with frequentist formalism. So how about we treat the number of bits that we need to scrub, and we're going to call that M, as a random variable, as a function of the same underlying event that gave us the quantum bit error rate. And furthermore, what if we set it up, the construction of this random variable M, so that the probability that it's less than 2 root 2 times P, such that that is less than epsilon, well, then we win, right? The probability that we will have underestimated on any given trial, any given key negotiation, the probability that we will have underestimated Eve's information will be less than epsilon. And that probably sounds to a lot of us an awful lot like a confidence interval. And that's because that is exactly a confidence interval, except for one small detail, which is that it's one-sided. Usually, if you go to 538.com or wherever you're getting your polling information, they'll give you a 95% confidence interval, and it'll be symmetric. We only, in fact, care about the one side. So that's great. We just get Nate Silver on the horn, ask him whether we should treat this as a Poisson or a normal, and we're good, sort of. A couple of caveats here that I should call out is that one, binomial distributions do not admit convenient closed forms or computationally pleasant mechanisms for computing exact confidence intervals. you almost always wind up approximating them either as a Poisson or as a normal distribution, depending on how low P is and how many samples you have. Which for an engineering introduction, I think is sufficient. If you say, oh, it's about 10 to the minus 12, the probability that Eve will have more information, that's fine. But if you want to write a paper on it, you probably want to say, no, it is definitely less than 10 to the minus 12. So unless you're dealing with literature which is talking specifically about the limit, where you're dealing with infinitely long keys, you'll probably see them using different mechanisms. But hopefully this gets the gist across. Actually, I'm going to pause there. Any questions about parameter estimation? Okay, so then let's talk about what we can do to mop up our leak. We have an estimate for m bits that we need to scrub out, and we had n bits to start with. So can we just grab a hash function that goes from n bits of input and spits out n minus m? Certainly that's my first thought, having interacted with HMAX and HKDFs and other RFC standards for key extraction and message authentication codes. And good news, yes, we absolutely can. It totally works, subject to a couple of small caveats. First, our hash function needs to be chosen at random from a universal hash family. That random choice can be public, but it does have to be random. And then additionally, we're going to need to trim off 2 log 1 over epsilon bits, where epsilon is our acceptable distance from uniform of the final raw key. Thought of another way, we're going to allow Eve to continue to have epsilon bits of information. I don't think that's an exact definition, but roughly, we're willing to give Eve that little tiny negligible bit of information about our key. And if we're willing to do that, then we can in fact just choose our hash family, send across some seeds, and do the hashing, which is a direct consequence of a pretty well-known result called the leftover hash lemma. I do not have the time or talent to instruct us all in how that works here, certainly not in the time that we have allotted, but I have linked it in the slides if you care to go over how that actually is built up. But the upshot is fairly straightforward, right? Because our choice of hash function from our hash family can be public, and that doesn't break the leftover hash lemma, we can just announce a random seed. Has to be a long enough random seed, but can be public. And then we're both going to take that random seed, we're going to use it as a salt in our hash function, and we're going to hash the secrets down, and they're going to go from n bits to n minus m, and voila, Eve no longer has information on our secret. And that covers up privacy amplification. Any questions there? Alrighty, so the next thing, which we haven't addressed, and it's a doozy, is that Eve can literally man in the middle as we've set things up thus far. Alice and Bob are talking unauthenticated on open channels. If you imagine that Eve sets herself up with a receiver to catch all of Alice's laser pulses and sets up her own receiver to send new ones on to Bob, then she can just do QKD with Alice and with Bob. And okay, sure, they wind up with different secrets, but Eve knows both, and they're only ever talking to her. And you wind up not really with a not any sort of useful cryptographic scheme. You're talking to the assailant rather than the people that you actually need to be talking to. So we need some sort of authentication scheme, and we're going to need some sort of bootstrap secret that we can work with, which sounds really, really bad. But the good news is that we can still use this scheme practically as a mechanism for stretching our bootstrap secrets. For instance, to allow one-time pads to be used in the data plane. And actually, I'm going to ask a quick question. Is anybody willing to admit not having read enough trashy spy novels to know offhand what a one-time pad is? Really? Okay. I'm afraid I might have just put you all to sleep or lost connection, because I don't believe that. And I'm going to do a quick reminder of one-time pad because I assume people are just being shy.
I think you asked the negative if anyone was not familiar with a one-time pad.
Yes, I might have double negatived. Anyways, the idea behind a one-time pad is that XOR is really cool, and it has 2 really neat things for use in cryptography. One, it is its own inverse. If I XOR A with B, and then I XOR it with B again, I get A back out. The other is that if I take a bit string and I XOR it with some random string of bits, the output also looks random. And that's because if I XOR with 1, that looks like a negation. And if I XOR with 0, that's the identity. So if I randomly choose to XOR with 0 or 1, I'm randomly choosing either to let a bit through or to flip it. So that's your perfect 50% corruption probability. And this allows us to create a very simple but very, very powerful encryption scheme by just saying, okay, Alice and Bob, you both have shared secrets that are good and random. And Alice, when you want to send a message to Bob, just pull some of your secrets, some of bits off that secret, XOR them with your message, send it over the wire. Bob will XOR it when it gets there, and nobody in between will be able to tell anything other than that looks like noise. The downside to a one-time pad is that while it is perfectly secure in an information theoretic sense, it does not involve any sort of tractability arguments. It's wonderful. You have to throw away the bits of secret that you use. You only get to use them once, hence one-time pad. And since our goal is unconditional security here, we're not going to be able to use a standard HMAC. We're going to have to use something sort of like those one-time pads. And specifically, we're going to construct a one-time MAC. So what we're going to do is we're going to take our bootstrap secret and we're going to pull a chunk of bits off of it. The size L bits is going to depend on the size of messages that you want to be able to authenticate. And we're going to choose, again, a member of a universal hash family. And we're going to hash that message down into an M-bit message tag, which we will encrypt with a one-time pad. Those bits from the one-time pad, of course, we have to discard. And we send that over to Bob. When Bob wants to verify the message, he decrypts the tag with some bits from his one-time pad, the same corresponding bits to the ones that Alice used, of course. And then he computes the same hash function. If the tags match up, great, we're good. Okay, why does a one-time MAC work? The core piece here, there are really two things. First, Eve doesn't even know the hash that's being used for the messages. We didn't just announce a seed to use to select our hash function. We used a secret, and this is really important because if Eve can manufacture hashes, she can take a message that has a one-time pad, a one-time MAC attached. She can compute the tag, XOR it with that MAC, and now she gets the one-time pad out, and she can use that one-time pad on another message which she has computed from scratch. So Eve can't do that, thankfully, because she doesn't know what the hash is. And moreover, because the hash value is encrypted and perfectly encrypted, she can't really hope to manufacture a hash collision. And that leaves her with really one out, and that is she can guess. She can say, you have M bits. Well, I'm just going to choose M random bits. I'm going to tag my message with that, and I'm going to hope that Alice likes it, or Bob likes it, whoever is doing the verification. And trivial counting arguments tell us that's got a 1/2 to the M chance of success. This places a bit of a trade-off for us between how much key we're willing to expend on each of our messages and the probability that Eve is going to be able to successfully impersonate us. You can imagine that if we're using 1 bit, then Eve has a 50% chance. That's no good. But if we're using 256 bytes, that's using a lot of secret key for every message, and that's going to mean that our quantum key distribution is going to have a much harder time stretching our key, and in fact, it might run in the red rather than in the black in its balance sheet if we make it too large. So a common choice here is 5 bytes, which corresponds to about 10 to the minus 12 chance, but is still a manageable amount of key to use for each of your messages. All right, any questions there?
I'm not sure that I recall all the pieces of information that are publicly available to Eve, but is there any advantage to taking any of these public announcements, such as like with the intent to like decrease epsilon, like the bound on epsilon, by actually just using a classical encryption scheme to make those a little harder to, or less likely to be recoverable?
So that might be practically useful. Nobody in the literature discusses any such thing because we were assuming that Eve is closer to Laplace's daemon than any live, than she is to any sort of live, real computational entity today. We assume that she can, with a snap of her fingers, crack any code for which tractability is the argument why you can't. We assume she solved P equals NP. We assume she has a million petaflop processor that she's working with. Any assumption you want to make, we're assuming here that Eve can do it. So it wouldn't do any harm to slap classical encryption on some of these things, but the security proofs don't depend on it. And because we're successfully getting negligible risk with plain text communication, it's not really something that's been looked into much.
Got it. Thanks.
Okay, so our last attack that we're going to cover here is photon number splitting. And again, photons are hard to work with. This time, though, it's not going to be that they have a tendency to get flipped. Our problem with them now is that it's actually hard to create exactly one photon. Ideal photon sources are being researched, but they're certainly not popularly available. So what most experimental setups will do is they will take a laser pulse and they'll dim it down to approximately one photon. And more precisely, the photon pulse will be Poisson distributed with some mean less than 1. So usually the pulse actually doesn't even go out. Then the most likely number after that is going to be exactly 1 photon, but there's still a chance of 2 or 3 or even 4 photons being included in a single pulse. And this is a big problem for us because all of our arguments for correctness and for security depend on the fact that if Eve is interacting with these photons, she has to have some chance of inducing error thereby. And if she has multiple photons, then she can just kind of pluck one off the top and leave the rest to go through undisturbed. Those assumptions break down completely. And what's worse, Eve can theoretically preferentially block single photon pulses. And because Alice and Bob are expecting not all of their photon pulses are going to get through, say if you're shooting a laser through atmosphere, if it ever hits an atom in between, that pulse is gone. So you don't expect all of your pulses to get through, and you can, in a number of experimental setups, have fairly high loss rates. So doing this won't necessarily set off alarm bells, but it will further increase the number of bits of information that Eve can steal without compromising herself in terms of intercept resend detection, like we discussed earlier. And this is called photon number splitting because you're splitting a number of photons apart to do your attack. And very briefly, the style of defense which is most popular for this is to start using multiple signal sources. So I'm going to call them S and S prime. S is your original real photon source. It's averaging mu photons per pulse. And then we're going to have S prime, which is a decoy state. And that's going to average more photons per pulse. The important thing here is that S is going to send more single photon pulses than S prime, and S prime is going to send more multi-photon pulses. And because Eve can't tell just from looking at a pulse whether it came from S or from S prime, if she starts preferentially blocking pulses from pulses with single photons in them, then she's going to induce more drop in S than she is in S prime. And we just said that. And what we can do then is we can compare the empirical transmission loss for things that were sent on S, things that were sent on S prime. And if they differ, we can conclude that Eve did something naughty. We can do calculations which are spiritually similar to the parameter estimation we talked about for intercept resend. But I'm not going to go into them here because I am right up against time. In fact, I'm 1 minute over time. So not going to go in that here, but you sort of get the idea, at least hopefully. So here's a TLDR, which I will let you read on your own. Hopefully that makes sense now. More stuff that you can read up on if you're interested. And a couple of images that were included. These are public domain images, but still I feel like being polite and saying these are where I got them. And that leaves us at questions. Really, we're completely silent?
No, I got one. I assume that your current work may or may not be related to this space.
Some of my current work is related to this space.
Awesome. That is fabulous.
If you fill in current upper bounds for the half dozen parameters you provided, just how many photon bits do you need to have to send a secret key bit? Or from the point of view of what's the ratio of successful bits delivered compared to your notional single photon source being kicked?
Yeah, so that's I actually don't know that number off the top of my head. It's not high. Or rather the number of photons you send compared to the number of bits you get is very high. So your yield is pretty low. And that depends on a lot of factors. Depends on how good your either fiber or laser is. Depends on how you've got your QKD post-processing tuned up. Depends on more things that are not coming immediately to mind, but it's a laundry list of things. What I will say, sort of in answer to the spirit of your question, I think, is that practical experimental QKD systems, and I think the most advanced today are being built by Chinese entities. They report rates of key generation on the order of bits per second, maybe kilobits per second, and they're really impressive systems. So this is not a straightforward thing if you want to say encrypt the data leaving YouTube. The scales are not even close to being right.
Thank you.
Anybody else have anything? All right, I'm going to give a 5 count since this is the very end, and then after that, I think we can stop recording. 5, 4, 3, 2, and 1. All right. That concludes the talk.